Episode of Mr. Avila Physics. Today we're going to be talking about kinetic energy and the work energy theorem. Now, energy is one of the most important concepts in science. Okay? And in physics, we define energy as the ability to do work. Now, in this video, we're going to focus on only one type of energy, which is kinetic energy. Kinetic energy is defined as the energy of motion. If an object is moving, then that object has kinetic energy. So, a moving object applies a force on a second object if it hits it. Take, for example, a cannonball hitting a brick wall. When the ball hits the wall falls. Another example could be a hammer hitting a nail. Right? The hammer hits a nail, the nail moves into the wood. Now, in both of these cases, we have a moving object that when it comes in contact with the second object, it applies a force, right? So when the hammer hits the nail is applying a force on the nail, and the nail moves. So that means that since the hammer is moving, then that hammer has the ability to do work on the nail, right? Because it applies a force and the nail moves a certain displacement. So then we can say that an object in motion can do work on a second object. And an object in motion, therefore, has energy. In this case, kinetic energy. Now let's see how work and kinetic energy are related. So take, for example, a car accelerating from V1 to V2 over a certain displacement. Right? In this case, we have a net force that is being applied on the car through a certain displacement. So that means that this force is doing work. And the work is going to be equal to force times displacement cosine theta. In this case, the angle is 0, which means that cosine 0 is equal to 1, which means that the net work done by the force by moving the car at displacement d is equal to F net times d. Now let's analyze this example a little bit deeper. So we know that work is equal to force times distance. We also know that net force is equal to mass times acceleration. Now let's find out the acceleration of the car. So the acceleration of the car will be found by using this formula. So the car undergoes a certain acceleration to change its velocity from V1 to V2. If we rearrange this formula to solve for acceleration, we get that acceleration is equal to V2 squared minus V1 squared divided by 2d. Now, let's combine all this. So, once again, we know that work is equal to force times distance, and force is equal to mass times acceleration, right? So this right here is our net force. Then for acceleration, I'm going to substitute this value right here. So I'm going to take this value of acceleration and place it in that equation, and we'll get something like this, right? Then simplify what we can, and we get this, right? And what we can simplify is, of course, cancel the displacement. Then we expand and we get something very important, which is this formula right here. So net work is equal to 1/2 m v final squared minus 1/2 m v initial squared. Now this quantity right here, the quantity 1/2 mv squared, this quantity is going to be defined as kinetic energy. So the quantity 1/2 mv squared is defined as the translational kinetic energy of the object. So we can say that the kinetic energy of an object at a certain time is equal to 1/2 mv squared. Now, that means that our equation that we found, network is equal to 1/2 mv2 squared minus 1/2 mv1 squared, we can rewrite this as kinetic energy 2 minus kinetic energy 1. Or we can also say final kinetic energy minus initial kinetic energy, which is another way of saying that network is equal to the change in kinetic energy. Which brings us to something very, very important. And that something is the work energy principle. The work energy principle states that the net work done on an object is equal to the change in the object's kinetic energy. So, by doing work on an object, we change the kinetic energy of that object. If the kinetic energy increases, then the work done is positive. If the kinetic energy decreases, then the net work done is negative. Okay? All right, so let's look at an example. How much net work is required to accelerate a 1,000-kilogram car from 20 meters per second to 30 meters per second? Pause the video here, take a couple of minutes, and see if you can solve this example. All right, welcome back. So, from the work energy theorem, we can say that the net work is equal to the change in kinetic energy, which is 1/2 m final velocity squared minus 1/2 m initial velocity squared. This is equal to 1/2 m times bf squared minus bi squared. This is equal to 1/2 m times bf squared minus bi squared. And this is equal to, take out our calculator here, 30 squared minus 20 squared times 500 gives me 250,000 joules. So the net work necessary to accelerate this car is equal to 250,000 joules. Here's your the textbook solution for this, okay, which is the same. And let's look at a different example. A car traveling at 60 kilometers per hour can brake to a stop in a distance of 20 meters. If the car is going twice as fast, what is the stopping distance? Now, in this case, we're of course assuming that it is the same car with the same tires, same brake on the same road. So that means that the braking force is the same in both cases. So let's see. Here we have that the net work done on the car is going to be equal to the change in kinetic energy. So this is going to be equal to 1/2 m bf squared minus 1/2 m vi squared. Since the car is coming to a stop, then the final kinetic energy is 0. So that means that the net work is equal to minus 1/2 m vi squared. And here we see that the net work is equal to net force times distance is equal to minus 1/2 m vi squared. So then distance is going to be equal to 1/2 m vi squared divided by net force. But Mr. Avila, what happened to the negative sign? Well, our net force, since it's a braking force, it also acts in the opposite direction of displacement. So force is negative. So the negative sign here and the negative sign with force will cancel each other out. But the important thing to realize here is that the stopping distance depends on the velocity squared, right? Because 1/2 is the same, the mass of the car doesn't change, the braking force doesn't change because it's the same brakes, the same tires on the same road. So the only thing that would change is VI squared. So if we're going twice as fast, then distance 2 is going to be equal to 1/2 m 2v squared over f net. This whole thing is the same. So distance 2 is going to be equal to 1/2 m 4v squared over f net. So distance 2 is going to be equal to 4 times 1/2 mv squared over f net. And this quantity right here in parentheses, this is our initial distance of 20 meters. So that means that if we double the velocity, then we are quadrupling the stopping distance. And let's see, this is how your textbook solved it, right? And hopefully this example made sense, and now we can understand the work energy theorem. Thank you all for watching, and I will see you next time.